Hey, how's it going? So, I'm making this video to teach people about powers of complex numbers and radicals of complex numbers. So let me share my screen. And as usual, you would take notes as if I was writing on the whiteboard. I'll do some examples. You can all try some examples. And then we're good to go. Oh. All right, let's see. All right, so we learned about arithmetic, and then we did polar and exponential forms. And now we are ready to go on to do powers of complex numbers, things like a plus bi to the n, and also roots of complex numbers or radicals, things like this, like that. This one isn't so bad. It's relatively easy. This one is kind of hard. Some will say not so easy. But we'll see what we can do. All of my notes are already posted, so you can take a look at those as you need to. Let's see. So now that we have learned about the basic arithmetic operations, learned about the basic arithmetic operations like addition, subtraction, multiplication, and division, we can now learn about powers and roots. So we will now learn about powers, which are like this: a plus bi to the power n, and radicals, oops, which are like the nth root of a plus bi. And so we'll start with powers. So let's look at my notes to get some motivation, because I don't want to write it all down. But check this out. Consider the following simple illustrations. If I asked you to do 2 plus 3i squared, you might say, you know what, that's easy. I just have to multiply them together like this in blue. I FOIL it, I simplify, and I get this blue answer over here. No big deal, right? But then I ask you, okay, what about this next one? 4 minus 7i now to the cubed. You know, it might take you a while. You'd have to multiply it out 3 times, but if you did the math, you would get this yellow answer down here. Negative 524 plus 7i. No big deal. Maybe it takes you a little bit longer. And then I ask about this one, which is to the power of this green 4 down there. That's going to take you a while, right? But ultimately, you would get this green answer. And you can see how as you increase the power from this green 2 way up here to this green 3, and now this green 4, and then maybe to the power of 5, you know, you kind of see that it gets harder and harder as we go. And you don't want to even bother doing the power of 5. Perhaps there is an easier way, and as it so happens, there is an easier way. It's easier to do this kind of power computation in polar form, and there is a formula or theorem that we can use to do so. So let me write all that down. So maybe I'll just say In order to compute powers of complex numbers, it is easiest to do so in polar form. And we use the following formula or the following theorem. It is easiest to do so in polar form due to the following formula. And it has a name. It is called de Moivre's theorem. Some guy in France a long time ago, de Moivre's theorem, made this formula. And here's what it looks like. If you had a complex number in polar form like this, r angle theta, and you need to raise it to the power of n, as it so happens, to apply that n exponent, you can simply apply it to the r like this, and then to the angle as multiplication, like that. That's how you do it. You can also do it in exponential form. So if you had r e to the power of I theta, and you wanted to raise this to the power n, similarly, it would be like r raised to the power n, e to the I times n theta. So that's how we do it. Usually we just use the first version because writing things in polar form is a lot easier. Plus we get to work in degrees. So usually we use this version. Okay. Here's some examples just to illustrate. So some illustrations. Let's say you had to do, for some reason, 3, and then the angle was 60 degrees, and you wanted to raise this to the power of 4. Well, according to that formula up there, this yellow one, right? What you would do is you would apply the exponent to the 3 like that, and you would multiply it onto the angle like that. And then you can use a calculator. 3 to the 4 happens to be 81, I think. 4 times 60 is 240, and there we go. You have just applied de Moivre's theorem. Just as another example, let's say you had 2 angle 150 degrees to the power of 7. Same thing. The 2 would get raised to the power of 7. And then you would do 7 times the angle, 150 degrees. 2 to the 7, 2, 4, 8 was 128. 7 times 150, 150 times 7 is 1050. 1050 degrees. So there you go. That's how you use this yellow formula up here. And that's how we're going to take powers. So the steps are, we convert our complex number into polar form. We apply the blue exponent using this de Moivre theorem, and then we convert back to rectangular. So let me write that down. and then we can look at some examples. So here are the steps for computing maybe we'll say for computing the power of a complex number. A plus bi all to the power of this blue n, like that. And n has to be an integer. I mean, it doesn't have to be an integer, but for our purposes, we are going to say n is a positive integer. So here are the steps. 3-step process, not too bad. Convert the inside, the a plus bi, to polar form, r angle theta. Step 2, apply de Moivre's theorem. Step 3, convert back to rectangular. So that's how we do it. Let me show you an example. And maybe I'll just take this straight from my notes. 2 plus 3i to the power of 5. So I want to compute this guy. Once we are ready, okay, so let's see. We just follow the steps. Step 1, convert to polar. So first, convert to polar form, which we've had lots of practice already, right? Draw the picture, find r, find theta. So this picture, pretty simple. There we go, real axis, imaginary axis, something like that. Drop the perpendicular, a equals 2, b equals 3. There's my picture. And so r is via Pythagorean theorem, right? Square root a squared plus b squared. A is 2, b is 3, so 2 squared plus 3 squared. 4 plus 9 is 13, so root 13. Theta, in this case, because we are in quadrant 1, it is precisely equal to whatever this green reference angle is. And we saw in the past that this is just tan inverse opposite over adjacent. So tan inverse of opposite over adjacent. And in this case, as it so happens, it is very important to use all 9 decimal places. And we'll see that at the end, why it's important. Make sure my calculator is in degree mode. Whoops. Tan inverse of 1.5 is, what is this? 56.30993247 degrees. Oh, excuse me. So there we go. Step 1 finished. I've converted to polar form. Let me write down the result. We have figured out that 2 plus 3i in polar form is the square root of 13, angle 56.3 degrees. Now, very important, this angle right here, I'm not actually rounding it. I need to use all yellow decimal places whenever I do the computation. I'm only writing down this green 3 just for convenience, because I don't want to have to write down all of the yellow decimal places again and again. So that's just for my writing convenience. So we got that. So next, we can apply De Moivre's theorem. Right? That is step 2. So now we apply the exponent of 5, right? Way up there, we have this yellow 5. Exponent, I'll just use blue. We apply the exponent 5 via De Moivre's theorem. Like so. So here's how you want to do it. You would do 2 plus 3i all to the power of 5. Well, that's going to be the same thing as our polar form, root 13, angle 56.3 degrees, all to the power of 5. And now I know, according to De Moivre's theorem, I can put the 5 as an exponent, and I can multiply the angle by 5 as well. That's what I need to do. So it would be root 13 to the power 5, angle 5 times, right? 5 times 56.3 degrees. So the radical, I'm just going to leave it as 13 to the 5 over 2. I don't need to compute it yet. I'll do that at the end. But for the angle, I am going to take my angle way up here in yellow, and I'm going to times it by 5. And according to my calculator, I get 281.5496 degrees. So that's what I get. And you need to use all of these decimal places. So there we go, step 2. Step 2 done. So technically, this guy is the answer, right? But we always prefer to have our answers in rectangular form. And do we know how to convert from polar form to rectangular form? Hell yeah. We just converted using cosine sine, right? So let me say finally, converting back to rectangular form yields the final answer. So let's do it. So we have 2 plus 3i to the 5. This is 13 to the 5 over 2. Angle, maybe for convenience, I will just write down 281.5, just so I don't have to write down the whole thing. So we're going to have 13 to the power of 5 over 2 times big bracket cosine. Did I make a mistake? What the hell? Did I not times by 5? Divided by 5, 56.3099 times 5 is 281. I think I made a mistake in my lecture notes, actually. Yeah, I'm not sure what I did there, so I'll have to go back and fix that. But I think we're okay. So, continuing, 281.5 degrees plus I times sine 281.5 degrees. You can FOIL if you want, like you can show the step. So you would do like boom and boom, totally fine. 13 to the 5 over 2 times cos 281.5 degrees plus I times 13 5 over 2 sine 281.5 degrees. Now, check this out. Extremely important. Let's say I put this yellow guy in my calculator just like it is. Okay, and I do 0.5 cosine times 13 to the power 2.5. What I get is I will get 121.482 blah, 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 right? If you put directly. But let me use all of these blue decimal digits way up there, and then let's see what happens. So all of those decimal digits in blue, cosine of that, times 13 to the power of 5 over 2 equals exactly 122. Oops, 122. Exactly, as an integer. And so that's the importance of using all of these green decimal digits up here. If you don't use all the decimal digits, you will get this green inaccurate answer. But if you do use all of the green decimal digits, you will get the precise integer answer of 122. So it's really important to do that. Otherwise, your answer is going to be wrong. Okay, so let me delete all of that. And I already forgot. I guess this was 122. Sine of 281.5. I think that's going to be minus. Sine times 13 to the power of 2.5. Negative 597. Negative 597i precisely. So there we go. That is how we do that. All of this blue stuff turned into this. And all of this black stuff turned into that. So there we go. That is how we, excuse me, compute the power of a complex number. Let me double check my answer. And yeah, sure enough, that's correct. So here you go. Hopefully you can see all of that properly. Okay, there. That's how we do it. Here we go. So again, step 1, and we're just following these 3 steps up there, right? Convert to polar form, apply de Moivre theorem, convert back to rectangular. And that's what we did. Step 1, we converted to polar form. That was this yellow result. Step 2 in blue, apply the exponent of 5, which we did using de Moivre's theorem. That resulted in this blue polar number down there. And de Moivre's theorem was from here to here, from there to there. Right? R angle theta to the power n is r to the n, angle n times theta. And then finally, in green, we convert back to rectangular form, making sure we use all 9 decimal places to get this precise green integer result down there. And one final thing, the only reason we get integers is because we started with integers, okay? So for example, let me just go to the side here. So just scrap paper. No need to write this down. If you had to do 2 plus 3i to the 5 manually because you pissed me off and now I'm giving you this as punishment, you would have to do 2 plus 3i times 2 plus 3i times 2 plus 3i 5 times, right? You know, maybe it wouldn't take you that long. Maybe it'd take you like 10 minutes, 15 minutes. It's not a big deal. But surely you would agree that if you were to FOIL all of this out, however you want to FOIL it, right? Certainly you would get integer results, right? Because all you would be doing is multiplying 2's and 3's together. So you have to have some integer results, right? You're not going to get fractions all of a sudden. You're not going to get decimal numbers. You're not going to get radicals. You will only have integers. That's the reason. And so going back to this question, we have 2 plus 3i to the 5. These blue guys over here are integers. And so when you do your computation at the very end, you had better finish with integers as well. And that only happens if you use all decimal places in the very end. Okay. Okay, cool. So why don't you all try an example? Why don't you try, I guess, this one. This is straight from my notes as well. -3 plus 5i to the 6. Maybe we should do a different one. Why don't we do, here, let's try this one. 2 minus 7i, maybe to the 8? Is that going to work out? 2 minus 7i to the 8. Kind of large. 6. Yeah, sure. 2 minus 7i to the power 6. So try this one out. Pause the video. Take however long you need to take to figure this out. And then we will do the solution together here on the screen. Okay. Okay. So let's see. Solution. First, convert to polar form. So this guy, 2 minus 7i, I believe is in quadrant 4. 2 minus 7i, maybe like that. Drop the perpendicular. A equals 2, b equals negative 7. This is my r. That's my theta. And then this inside guy is always reference angle. So I compute r using Pythagorean theorem, a squared plus b squared. 2 squared plus brackets, negative 7 squared. What is that? 49 plus 4? So square root 53. And then theta, because we're in quadrant 4, is going to be 360 minus the reference angle, which for complex numbers is always tan inverse absolute value b over a, opposite over adjacent. So 360 degrees minus tan inverse absolute value of negative 7 over 2. So the absolute value just gets rid of this negative sign here, right? Pretty much. If you put this in your calculator in degree mode, 7 over 2 inverse negative plus 360, it looks like I get 285.945 3959 degrees. So there we go. That's what I get. Step 1 is done, but let's write down the result. So we found that 2 minus 7i in polar form is root 53, and the angle is, let's just say 285.9 for convenience. Step 1 done. Step 2, apply this apply this blue exponent 6 way up there using de Moivre's theorem. So now using de Moivre's theorem yields 2 minus 7i to the power of the blue 6 equals root 53. Oh my god, that looks terrible. Root 53, angle 285.9 degrees, all to the power of the blue 6. So the 6 goes on to the root 53 as an exponent, and it goes on to the angle as a multiplication, 6 times 285.9 degrees. And I can use my calculator. Square root to the power of 6 is just cubed, right? Because over here on the side, if you had root 53 to the power of 6, that's the same thing as 53 to the half to the power of 6. Using our exponent laws, you would do 1/2 times 6, which is 3. So that's how I got that 3 right there in the exponent. Okay. Like that. And the angle, using all of these yellow decimal digits, I got to times it by 6, gives me 1715.672375 degrees. So that's what I have. So step 2 done. I have applied de Moivre's theorem. And now, step 3, I convert this guy back into rectangular form via cos and sine. So let me say finally converting back to rectangular form. Let's see what we get. 2 minus 7i to the 6. Currently, we have this. Let me just write 0.6 for convenience. I need a big bracket and then cosine plus I times sine. Right? This is how we convert from polar to rectangular. I suppose you can do foiling if you wish. You can expand like that. If you want to show your work, that's totally fine. $53 cubed. That's a big number. Sine 17, 6 degrees. Okay, so I should get integers, right, in the end. So using all of these yellow decimal places up here, cosine times 53 cubed is, well, my calculator gives me 14,714.999999, so 14,715. And then for sine times 53 cubed, this one gives me exactly negative 148. Ha, 148, 148. That's funny. There we go. Easy peasy, right? And we just followed the steps. So there we go. Take a look. Step 1, convert to polar. Step 2, apply de Moivre's theorem. Step 3, convert back to rectangular using all of the decimal places. Because we had decimals to begin with. If the angle was a nice angle, like way up here in green, if this angle was like something on the unit circle, like 240 or 210 or 300, then we wouldn't need to use decimals. We would do everything exact. But in this case, we did have decimal angles, so that's okay. Okay. What time is it? 7:42? I don't know when I started. What should we do? Let's see. What if I do 1? Yeah, I think that's all right. So we did 2 examples of converting from, of computing powers, and all of them just required using this yellow de Moivre theorem. That's all. And here were the steps. So these yellow guys are the steps. And oops, here are 2 examples. Example 1, example 2. It looks like I have more examples in my notes, the solutions for which I still have to fill in. So I'll fill those in as well. And then you can try those if you think you need to. which you should anyway, honestly, just to get the practice. But let's move on to radicals of complex numbers. And I think I will start a new video for that. So thanks for listening. I will see you next time. Oh. Dude. All right, see you later.